Okay, in the preceding, we were actually looking at the C1 question. The C2 question asks the same thing with the same numbers, except that in this case, the ball is hitting at an angle of 60 degrees with respect to the normal direction. Now, normal is perpendicular, so here's the normal direction. And the ball is hitting at 60 degrees, so that's like the ball coming in here and hitting down here. Does it hit as hard? You might think about that, but I want you to try to answer that question, okay, before you look at anything else that I've done. Okay, and I'll drop a hint here, so pause if you don't want the hint. Best to think about it, but here's the hint. Momentum is a vector quantity. You got to treat the momentum as a vector. It's got an x component and a y component and a z component if you're in 3 dimensions. But you can model this in terms of just 2 dimensions, just knowing that you're at 60 degrees to normal. So you can take that as a hint. If you need that hint, pause again, think it through a little bit. Okay, well, I'm going on now, so you should have paused. The point is that the momentum of this ball is not going to change in this direction. The ball is just going to keep moving in the vertical direction with the same speed. The only change is going to be in the normal direction, the direction perpendicular to that wall, so that you only want to consider the momentum in the direction perpendicular to the wall. I think it was Will came up with the unit circle. Okay, well, here's a picture of the unit circle. Here's a picture of a vector at 60 degrees to the x direction, and here's a picture of its component in the x direction. And for 60 degrees, you should be very familiar with those basic angles. That component is going to be half the magnitude of the vector. So what you end up with is only half the magnitude of the momentum change that you would have in this case. So that px is going to be p cosine 60 degrees is 1/2 p. Okay, so you're going to have half the momentum, and that's going to give you half the momentum change, and therefore half the force. Now, we're still assuming that we're colliding with these walls at each wall 15 times per second. That means, among other things, we're going to have to move these walls twice as close together as they were here. We never said how far apart they are. You can figure out how far apart they'd have to be, moving at 4 meters per second to hit each wall 15 times a second. These walls would have to be twice as close. And we could even close this thing off, okay, so that the ball comes out here, hits this wall, then reflects back here, hits here, and maybe bounces off here, so it comes back down here and hits, and keeps following this sort of a path. We're only worried about what happens at any given wall. At each wall means we think about one wall. So we think about this wall, or we can think about this wall. Now this gets us more in the line of analyzing what happens, for example, to cause pressure in this bottle. Okay, in this bottle, you don't have just one 10-gram ball moving at 4 meters per second. What you have is you have an unimaginable number of molecules bouncing around in here and moving at speeds in the hundreds of meters per second. And they bounce off of each other, and they bounce off of the walls. In the process of bouncing off of each other and off of the walls, their directions become randomized in space so that you have as much kinetic energy in the x direction as in the y. Well, let's say y is this way, and in the z direction. That results in the force that you would have if the balls were just bouncing, if the molecules were just bouncing back and forth between 2 walls. It's going to effectively give you 1/3 of the force, and we'll work out the details of that. Right now, I just want you to have the concept. So we actually split the momentum change into 3 components, and only one component applies to any given direction. That's something you want to think about, and there'll be questions very soon to get to that idea and address exactly why the energy and the force and everything partitions equally into the three directions. For right now, this question is preparing you for the idea that if the momentum is not perpendicular to the wall, you get less momentum change.